Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 4 of the distribution of random variables of the biostatistics subject. In the previous video, we have completed the binomial distribution, and in this video, we are going to complete the Poisson's distribution. So, Poisson's also is a scientist, okay, and his assumptions for Poisson's distribution, okay. His assumption is based also in some criteria. Here we'll talk about 5 criteria, okay. The properties of Poisson process is, the first thing is for individual objects, okay, of observation. For example, observation of the people or whatever. If I'm observing the people, there are 2 outcomes, okay, either happened or not happened, occurred or not occurred, okay. The second one, the occurrence of events are independent. One of the very common or famous examples of this Poisson's distribution, because Poisson's distribution mainly on the assumption or the concept of we having something happen over a long interval or a long period, okay. So it is not one time or one instance happening, it's over a period of time. For example, I have some cars which passing through a street. I'm standing here watching cars, and they have cars passing here. So how many cars, or the probability of having hundreds of cars passing from this street in 1 hour, okay. So if I change my interval, say, okay, how many cars are passing in this street in 2 hours, it will be more than, we assume it will be more than 2 hours. 3 hours, it will be more than 1 hour, and it will be more than 2 hours. And if the number of cars are more than, so the probability of the specific number of cars can pass through the street, it could also be higher than, okay. So here, so if I have a number of cars passing in certain period of time, I said the number of cars passing in 1 hour is different from the number of cars passing in 30 minutes or 1 second or 2 minutes or 3 minutes or 1 day. So it depends on the interval, how the interval is big. So for example, if I have the first hour 30 cars passed or 300 cars passed, it doesn't mean that in the next hour less number of cars will pass, or less number of, or more number of cars will pass, because the first hour is independent. It has nothing to do with the previous hour or the next hour. So here the second point is the occurrence of an event. If the number, for example, I assume that 300 of cars are passing in 1 hour in the first hour. So if it happens, it doesn't mean that in the next hour lesser number will happen or more number will happen of cars will pass. So the occurrence of an event are independent. They are totally independent. Maybe I have 300 cars in the first hour and another 300 cars in the second hour, or 500 cars or 50 cars only. So there is no relation between, they are not correlated, okay? So the occurrence of an event, the occurrence of events are independent. And the probability of a single occurrence of the event in a given interval is proportional to the size of the interval. So the probability of having 50 cars passing within 1 minute, it is less than the probability of having 50 cars passing in 1 hour. It is lesser than the probability of having 50 cars at least passing in 1 day or 24 hours. So if we increase the interval, the probability will increase. This is the third point. The probability of a single occurrence of event in a given interval is proportional to the size of the interval. If it is the interval, the period interval is 1 hour, or the period interval is 2 hours or 3 hours. So as far as it's increased, the probability also will increase. So here the fourth property, theoretically, an infinite number of occurrences of the event are possible, okay, in interval of the observation. So we may have some interval of observation of 1 day, of 1 month, 1 year, 1 hour, 2 hours, whatever. So theoretically anything possible. So it could be the number of observation or the number of occurrences could be even infinite number, okay? 1 million, 2 million, 700 million, 1 billion, 2 billion, infinite number theoretically, okay? There's nothing called infinite number in reality, but theoretically it could happen because it depends on the interval, okay? Theoretically, an infinite number of occurrences of the event are possible in the interval of observation. On the other hand, an infinitesimally small portion, if I have a very, very, very minor or very small portion of interval or a very tiny portion of interval, the probability of more than one occurrence of the event is negligible. So we can consider it 0 if the interval is very, very, very small. We can consider it as 0. So this is called Poisson distribution 1. Poisson distribution 1. In the next slide, we are going to discuss Poisson distribution 2. So here in Poisson distribution 2, okay, for an event that is rather unlikely to happen, something unlikely means the probability is very, very small, maybe 0.0001. Okay, it's unlikely to happen, small probability. Okay, the event is rather unlikely to happen, but has a lot of opportunity. Large N is expected number of occurrence. So here, if I have an event that's rather unlikely to happen, it has a small probability, but it has lots of opportunity or large number, okay, of observations, then we cannot ignore it. It is not negligible. As we have taken earlier, the mean, okay, the mean equals n times the probability, the number of opportunities times the probability. This is called lambda. Lambda here means the mean, okay? So lambda means the mean of Poisson distribution, okay? Or called the parameter of Poisson distribution. So it could be either the parameter of Poisson distribution, which is lambda, or the mean of Poisson distribution. So if lambda, the mean number of occurrence of an event, if lambda is the mean number of occurrence, the average or the mean number of occurrence, or the parameter of Poisson distribution, its probability to happen 2 times or 3 times. For example, I said the mean number of the number of cars passing through this road is 300 cars per hour. For example, 300 cars per hour or 300 cars. Then the probability of having this happen 3 times, repeating or occurring 3 times, is given by this formula. So the probability of lambda, okay, happening 3 times or 4 times or k times, the probability of lambda happening 3 times equals the mean lambda of power k, okay, divided k factorial times e of power minus lambda. So just get lambda here, get lambda, and the power of lambda will be k. So lambda of power k divided k factorial times e of minus, usually when you find e of power minus something, e of power minus lambda, okay, where lambda equals mu, the population mean, the mean of the population. This is called the expectation value. Lambda is the mean or the expectation value, which is mu. Okay, the variance, which we said sigma square, equals lambda also. So let us look at this example. And this example say emergency admission at the hospital. Okay, how many people are admitting in the emergency section in the hospital are distributed according to Poisson's statistics. Okay, emergency admission average is mean. The mean or the average per day is 3. So I have 3 cases per day. It could be per hour, per minute, in different scenarios, but in this case 3 per day. So the interval is day. So I have 3 per day, which is lambda, because lambda is the average or the mean or the parameter of Poisson parameter or Poisson mean. Okay, so the mean or the average is 3 per day. So lambda equals 3. Okay, find the probability that exactly 2. It is not up to 2 or 2 or less. If 2 or less, we'll have to get 2, 1, 0. But here exactly 2. So k here equals 2. 2 admissions occurred on a given day. So lambda equals 3 and the k equals 2. I just write the formula here. The probability of, he said it is Poisson statistics of k lambda equals what? This one of power of this one. So it will be lambda of power k, just to memorize it. This is the way to memorize it. Divided k factorial Okay, this is not part of the question. Okay, factorial times e of power minus, usually e of power minus lambda. Okay, because I have used k here, so this time I use lambda. That's it. So I just compensate in it. K, lambda is 3, power k is 2 square, k factorial, 2 factorial, e of power minus 3. On the calculator you can get it. You have to try it before the exam, so be familiar with e of power minus something and how to type it on the calculator. So the answer will be 0.224. This is the probability of having exactly 2 admissions per day if I used to get my average 3 per day. So this question was a very direct question. So coming to the next example. So in this example here, the emergency admissions are still distributed according to Poisson statistics. So still using the Poisson statistics, any person has a chance of 1 in 50,000, very small, very minor probability. 1 in 50,000, okay? So it is very minimal, it's remote probability. It's unlikely to happen, okay? So it's around 0.00004 zeros, then 2, okay? Very small probability, okay? So it should not follow actually Poisson statistics, but if you remember in Poisson statistics, there was 2 conditions here were put. The second condition here, that in the event which is unlikely to happen, but it has a lot of opportunity. So the number of population, the number of sample is very big. So also still we cannot ignore it. We cannot say it is negligible. It still can happen. And this is actually example on this problem. So emergency still distribute according to Poisson statistics. Any person has a chance 1 in 50,000. So 1 divided 50,000. So probability is 0.00002 to have an emergency case during 24 hours period. The city has a population of, which is N. N is 150,000, so it's very big population, so it is more than the chance. Okay, the chance 1 in 50,000, but here I have 150,000. Even so, it is 3 times of this one. So there's a big opportunity here because the number is big number. The population is big. Okay, the city has a population of 150. Find the probability that exactly 2 emergency admission occurs on a given day. So he's asking about exactly 2 cases. So K, in this case, K equals 2. So K in this case equals to exactly 2. K equals 2. So what about lambda? Lambda is the mean or the average. I don't have it. He didn't give it to me in this example, the average. So how can I get it? I said that lambda equals NP, the population times the probability. I have the probability because he said 1 in every 50,000. So this is the probability. Okay, so 1 in every 50,000. Then N is 150. So lambda equals 150,000 times the probability, which is 0.00002. Okay, so it will give me 3. So lambda equals 3. This is the mean or the average. Okay, the average of the distribution is 3. So now I have K equals 2. I have lambda equals 3. I have N equals 150,000. So can I solve this problem? Yes. So the probability of K lambda equals probability of K equals 2, lambda equals 3. It will equals the first one, lambda of power K divided K factorial times E of minus. I used K here, so lambda. Just I'll substitute in it, as you can see here. Probability of lambda K equals 2, lambda equals 3. So lambda of power K, okay, divided K factorial. So times e of power minus lambda. I just substitute them, 3 power 2 factorial, so the answer would be 0.224. This is the probability of it. So here we can see that Poisson and binomial, okay? What relates Poissonian and binomial? Always we can use the binomial as far as we have n and p. Okay, so we can use always binomial distribution. The calculation is little complicated for binomial because we have to use the combination and you have to use the p and the q. But as far as we have n and p, so we can use binomial. But we have in some cases there are some limitations, so we have to use Poisson. If n equals infinity or p limiting, n is as high as it's tending to be infinity, and p also it's tending to be zero, p tending to be 0, or n times p, which is lambda, tends to be lambda. Okay, so if np tends to be lambda, or p tends to be 0, or n tends to infinity, in such cases this will be limiting the case of binomial distribution. So the problem can be solved using Poisson distribution. Okay, any problem that can be solved using Poisson distribution, it can also be solved using binomial distribution, but subject to I must have p and n. Okay, p and n must be known. So any problem follows Poisson can be solved by binomial as far as I have p and n. Okay, so let us look at the previous example which we have taken in the previous slide on Poisson distribution. We already arrived to p because we know that one out of 50,000 cases, so the probability will be 0.00002. Okay, so we already got the probability. The question was asked about 2 cases to happen, and then was 150,000. If the probability is 0.002, this means that Q, which is the complementary 1 minus 0.00002, which will be 0.99998. Okay, so I can get Q as well. Okay, so here in the previous example, I have P, I have K, I have N, and I can calculate Q equal 1 minus P. So any person in the city during that day can have an emergency case, and this is its a probability. Okay, so what is the probability that 2 of them will have emergency? So I have K also equal to, so just I can take the same numbers and substitute in the formula of the binomial. So the probability, okay, of X equals K equals 2 in this case. K will be equal combination of NK P power Q N minus K. Okay, so we can substitute here on this formula. Okay, the combination we can put it N factorial divided N minus K factorial times K factorial, and P power Q power N minus K. It will remain the same. By substituting, we'll get the answer. Okay, so even the Poisson problem can be solved by binomial, but subject having P and N. So here also Poisson problem, also here that the problem that can be solved by binomial distribution can be also solved by Poisson. So I can use Poisson to solve the problem which is related to binomial, but subject to conditions here, which is mainly the basis of the Poisson, that n is very large. Okay, the population from where I picked the sample. So for example, it's 150,000. I picked a sample of 50 people, but the population 150,000. It's a big number, so n is large. Okay, the experiment is carried out on a large number, the population. Okay, the population from which the sample is taken is large, n is large, and the probability of the success or for the criteria which I'm looking for to happen, it is very low. Okay, the probability is very small, tends to be 0. In this case, if the probability tends to be 0 and the n is large, so in this case I can use Poisson. Okay, so these are the two conditions to use Poisson to solve the binomial problems. Okay, so what are the two conditions? N is large and B is very small. And in some cases also, it is not mandatory that B tend to be 0. Could be also Q tend to be 0. If Q not equal, tend to be 0. If Q tend to be 0 means that P is very big, very close to 1. If P is the probability is very close to 1, so in case of the probability is going to be 0, very close to 0, or very close to 1, I can use it. If the probability is very close to 0, okay, what happened? So I can use the Poisson. If the probability is very close to 1, this means that Q will be very close to 0. Because one of them should be closer to 0, P or Q. Alternatively, if P is large, P tends to be 1, the probability of P is very large, probability maximum will be 1. So if the probability is large, P tends to be 1, we can still use Poisson, okay? Poisson distribution, because in this case, Q will be equal to 1 minus P. B is very close to 1, which tend to be 0. So Q will be small. So either P or Q tend to be 0. I hope this is clear. In this example, we are going to see whether we can use Poisson or we can use binomial, and what is the difference. So we have two conditions, as we mentioned in the previous slide, for Poisson. Poisson, that N must be large, okay, and P small, okay. And to use binomial distribution, we must have N and P. So let us look at our example and see what we have here. So in this example, it said that we introduce the gene of GFP, tag the fluorescent protein into cells, okay? So we can investigate its subcellular localization with the microscope. The transfection efficiency is 1%, okay? So 1% of the cell carry the gene and express GF. So the probability is 1%, 0.01. I have P. Okay, let us see whether I have N also or no. If I have P and N, I can use binomial. P and N, binomial. So, and there are 100 cells. So I have N equals 100. Okay, what is the probability when we look at the microscope? Can we see at least 3 transfer? At least 3. Here is the trick. At least 3. This means that we can see more than 3. K should be more than or equal to 3. So usually when they say at least, so I should be, if they said at least, so I have to work the other way around. So I can get the probability of not seeing it 1, which is lesser than 3, could be 1, 0, 1, and 2. Okay, then say 1 minus this probability. If you remember the initial introduction of the probability, we said the probability of something happening, okay? If, for example, I said at least 3. So the probability of happening at least 3. So what I used to say, I say the probability of 1 minus, okay, it would be 1 minus the probability of having anything the other way around, less than 3, so 2. At least 3, so I have to check 2, 1, and 0, okay? The probability of 2, probability of 1, and the probability of 0. So if I get this 3 probability, this is the other way. I'm looking for at least 3. So at least 3 means 3, 4, 5, 6, 7, and so on. So if he said at least 3, I can get the other way around, which is not at least 3. 2 is not 3 at least, 1 is not 3 at least, 0 is not 3 at least. And I minus them. I get the other way around, okay? This is the way which we are going to use in this problem. So let us first see whether we have N and P and we can use the binomial or no. So as we said here that we have P equals 0.01, which is 1%, N equals 100, okay? K, it is not equal to 3, K is at least 3, so it's greater than or equal to 3. So since I have N and P, I can use the binomial. But here he is asking whether we can use Poisson distribution or not. So let us follow up the steps which they have mentioned here. P is 0.01, N this amount. If I have P and N, I can get lambda. Lambda equals NP, okay? So lambda will be equaling 100 times 0.01 equals 1. So here the question. To use Poisson distribution, I have two other characters. That n should be large and p should be small. So p here is small, but not so small, but it is small. So he's asking here, can we use the Poisson distribution, the borderline or the end of the story, case that p must be small, but it's not extremely small. It's not 0.001. It is only 0.01. Small, but not extremely small. But anyway, it is little small, okay? It is small. And the number of chances of occurrence is 100. 100 is not small, it's large also, but it's not so large. It is moderate, medium, okay? So he said here in the problem, let us try. So the probability of having k greater than 3, I cannot get greater than 3 because k greater than 3 equals greater than or equal to 3. This means that I have to count the k equals 3, k equal 4, 5, 6, 7, up to infinity, which I cannot do. So the other way, I work the other way around. How if it is not greater than 3 or equal 3, it will be k equals 2, k equal 1, and k equals 3. 3 scenarios only. Okay, so k, probability of k greater than 3, it will be equal 1 minus the probability of k equals 0 minus the probability of k equals 1 and minus the probability of k equals 3, or 1 minus the probability of k, okay, k equals 0 plus the probability of k equals 1 plus the probability of k equals 2. So just I can distribute the minus, the negative inside the bracket, just for you to understand. So the probability of this 3, the probability of the 3, and I have to minus it from 1, okay? So then I have to get the probability of k equals 0. I put the formula, okay? We just took it in the last page here, not this one. Okay, this is the formula we have. Let's just make it clear. Here, okay. So this is the formula. I can use the same formula here. Okay. So k equals 0 and substitute with k, and there was lambda. I have already got lambda here. Okay. I can substitute with them and put k with 0, so I get this answer. So the second one, I put k equals 1. Third one, I put k equals 2. Okay. And here, so here using the Poisson distribution, the formula of Poisson distribution, okay. So using Poisson distribution, we can use this formula, okay. So here, first time we'll put k with 0, so it will be lambda 1 of power k 0, okay, divided k equals 1, sorry, k equals 0 in this case, so k factorial, 0 factorial is 1, okay, times e of power minus lambda 1, okay, so we'll get this one. Then next time we'll put k equals 1, third time we'll put k equals 2, and we'll get the answer every time. Then we'll add them up, okay, and after we adding them up, we'll say 1 minus the total of them, okay. So the answer which we have got here of this probability, it will be 0.08, okay, 0.08, which is 8.03%. If we use the binomial, because we have already n and p, we can use the binomial. So we can get the formula also of the binomial here, which will be combination nk p of power k, q of n minus k. I have already p. I can get q, which is 1 minus. Okay, it will be 0.99. Okay, 1 minus 0.01. Okay, I have p and I have q. I have n. I have k. So I use it to get for k equals 0, and then k equals 1, and then for k equals 2, and then I use 1. I add all of them and say 1 minus the total which I got from here. So the answer, they found that it is 0.0794, which is 7%, 7.94. So here, using binomial way, it is the probability 7.94%, and using Poisson, it is 8.03, which very close. So they are approximately the same. There's no big difference between them. So approximately binomial Poisson was quite good, okay? Because the sample also is not so small, it is 100, and the probability is not so big, it is also small. It's not so small, but it's small, 0.01, okay? That's why the answers are very close.